A polarized ion source is a complex physical engineering device. Its operating principle can be explained using the example of the polarized deuteron beam formation. The source is fed with deuterium gas. Then there is a cell where the molecules of this gas dissociate into atoms. After that, these atoms, the atomic flux, move into an area of strongly dissimilar magnetic field, where, due to the Stern-Gerlach effect, the beam is divided into three components. The component with the required polarization type moves into the cell, where, through the interaction with the RF field, the exchange of spins takes place between electrons on the atomic orbit and the nucleon. At the last stage, the generated beam of polarized atoms undergoes ionization in a plasma ionizer. The plasma ignites in hydrogen. To generate polarized protons, hydrogen is added into the source entrance, while deuterium is used as the substance that creates ionization in the plasma. This way, a sufficiently clean beam of either polarized protons or polarized deuterons is generated at the output. Basically, this source may also be used to generate the beams of polarized helium-3 ions, but the unexpected intensity would be a lot lower. Depending on the requirements of a physics experiment, this mode may, in principle, be implemented too. The operating principle of such a source was proposed at the Institute for Nuclear Research of the Russian Academy of Sciences in Troitsk. Several such sources have been produced for scientific centers abroad. Based on the experience and with the participation of the actual developers of this source, a source of this kind has also been created at our institute. The major benefit of this source is the sufficiently high impulse current. It provides about 10 milliamperes of polarized beam current. The value of 10 milliamperes has, probably, already appeared a couple of times in my lecture. It is about the level of current needed for injection into the nucleotron for an effective use of its phase volume, its vacuum chamber. The source of polarized particles has already been used in 2 nucleotron runs, showing good parameters. The project parameters for the required accelerated beam intensity have not yet been reached, but we are aware of the ways in which this can be achieved. The requirement from the viewpoint of the polarized program of the NICA project is to generate a beam already accelerated in the nucleotron with an intensity of more than 10 to the power of 10 particles per impulse. This beam intensity is enough. Various sources may be used to produce the light ions of another type. For example, at our lab, a few laser sources for light ion generation were already created in the 70s. What is a laser ion source? It is a laser with an optical system. The laser beam is directed onto a solid target. The laser light is used for volatilization. Then, due to Townsend ionization, ions in various charge states emerge in this target. These ions are in the plasma expansion area. A plasma column builds up. This plasma column is given some time to drift in the plasma extension area. Next is the device that separates ion charge states and selects the required ones. Following after this device are instruments for ion extraction, which ensures the parameters needed for coordination with the subsequent devices. To obtain the defined charge state spectrum, it is necessary to determine the intensity of the laser radiation which, under certain conditions, accelerate electrons up to several hundred kiloelectron volts. These electrons in the plasma receive the required charge state. The higher the laser radiation power, the higher the charge state that could be attained. Basically, for the source to work, the minimum threshold limit value of laser power density has to be over 1 megawatt per square centimeter, which is easily achievable with modern lasers. The first laser ion sources at our institute worked on carbon dioxide, also referred to as a gas laser. To date, the technology of laser production has sufficiently developed, and new ions sources will be used within the NICA project, based on a solid-state laser, a neodymium garnet laser serially produced in the UK. The full energy in the laser radiation impulse amounts to around 2 joules, with impulse duration of 7 to 8 nanoseconds. This corresponds to about 5 times 10 to the power of 12 watts per square centimeter. That is around 6 orders of magnitude higher than the threshold limit value needed for the laser source to work. The laser source is quite simple in design. The main elements of this source are at normal atmospheric pressure. The working substance is located inside the target station. For instance, in the case of carbon ion production, it is a graphite rod. The main shortcoming of a laser source is the spread of beam intensity generated from impulse to impulse, and which may change several times. Something to do with the process of target volatilization and the process of plasma formation. Meanwhile, a laser source is capable of producing sufficiently high impulse currents. For example, fully stripped carbon nuclei may be generated with the use of a laser that we already have, with a strength of around 30 milliamperes and an impulse duration of up to 2 to 4 microseconds. Such a laser source has been used based on a solid-state laser during a run of the nucleotron. The same source has been used to test the heavy ion accelerator. In doing so, it produced carbon ions in a charged state of +2, resulting in a partially stripped nuclei. Carbon in a charged state of +2 corresponds to about the same charge-to-mass ratio to that of gold in the charged state of +31. To generate intense beams, let's say of lighter elements at our accelerator complex, a duoplasmatron source has been used and is projected to be used in the future. It is one of those sources that, well, after all, I am a physicist of a past generation for whom such sources seem like something that has always existed for centuries, and it's hard to even imagine that someone actually invented it and that it wasn't always there. It's like a quadrupole lens or a bending magnet. That means it's like some natural phenomenon. Despite that, this source type was invented by a very specific individual. It was Manfred von Arden. Right after the Second World War, he spent 10 years working as a contractor in the Soviet Union. He worked on the method of magnetic separation of uranium isotopes. For the implementation of this method, he was awarded a Stalin Prize. To generate intense uranium beams, he invented a new type of ion source. What are the benefits of this source? Firstly, in just a few words, I will explain its operating principle. Gas is fed into the working area. This source works mainly on gas mixtures. In case, for example, uranium ions are needed, one of the uranium compounds is fed into the working area that has a gaseous phase. Generally, such sources are used mainly for protons and deuterons, alpha particles, and when only hydrogen is fed, deuterium and helium. The plasma ignites inside the crossed electric and magnetic fields. After that, the plasma enters a special cell. When it gets normalized, its parameters get set, and it is from this cell where ions of the required type get extracted. Such sources are capable of generating an accelerated particle current of up to several amperes. Their design and technology of production are quite simple, and they are one of the indispensable elements of accelerators. Such a source meets all the demands of our complex for acceleration of ordinary protons, non-polarized protons, deuterons, and, perhaps most importantly, accelerated alpha particles needed for experiments, that is, helium nuclei. One may try to generate helium nuclei in a duoplasmatron, which are not available in other sources of the laser type, because there are no solid-state targets containing a sufficient quantity of helium.